Thank you everybody for joining today. So Tom gave a really nice introduction so that I can jump right in and tell you about the magnetic tail of Mars. I also appreciate your patience with this because I know we had to reschedule this webinar due to the government shutdown. So I'm excited to finally be here today and give you this presentation. All right, so starting with just a brief overview of what I'll be discussing with you. First, I'd like to give a background on planetary magnetospheres, and then I'll jump into specifically Mars and its magnetic space environment and what we're studying there. I'll tell you how we're using MAVEN to explore the Mars magnetic tail, and then I'll specifically go into some of the MAVEN data analysis and simulation results that I've been looking at and analyzing in order to explore the magnetic tail. Getting a little more specific into the physics, we'll talk about magnetic reconnection and how that's impacting what we're observing at Mars. And finally, I will cycle into talking to you about how the magnetotail or the magnetic tail relates to atmospheric escape, which of course is the main objective of the MAVEN mission here. So throughout this presentation, I'll scatter in a few questions that I essentially would like to answer as we transition into the different regions of this talk. So the first question is, how does a planet's magnetic tail form? And so in order to answer that question, I'd like to talk to you about planetary magnetospheres. So some planets have global magnetic fields that are generated through a conductive core. And if you see on the right here where my cursor is circling, this is an artist's rendition of Earth and its global magnetic field. So Earth has this dipolar magnetic field that is surrounding the entire planet, known as a global magnetic field. Throughout our solar system, there are several planets that have a global magnetic field such as this, and that includes Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune as well. But as you see on the bottom, we also have other planets without a magnetic field, with no magnetic field. And so at these planets, one may have existed in the past, but they're no longer present today. So a perfect example is what I'm showing you here, which is Venus. So we have two very different circumstances that we can come across in the solar system: a global magnetic field or no magnetic field. So now, as we continue talking about planetary magnetospheres and how they form, let's focus on the sun's solar wind. So the solar wind is a plasma, and a plasma is a gas that's filled with charged particles, and this solar wind plasma is produced in the sun's atmosphere. So the solar wind is going to stream out away from the sun at extremely high speeds, and that's because the atmosphere of the sun is extremely dense compared to space. So it diffuses outward, and it's going outwards at speeds of around 1 million miles per hour. Or as we use kilometers per second, that's the equivalent of about 450 kilometers per second. The solar wind also carries with it the sun's magnetic field, and this is important when it comes to our research on planetary magnetospheres. And we call the sun's magnetic field the interplanetary magnetic field. So for the most part, I'll refer to it as the sun's magnetic field, but if you ever see the acronym IMF, that's what I'm referring to, the interplanetary magnetic field. And on the right here, we just have a really nice picture of the sun, and you can see some of the solar wind streaming away and some solar activity going on at the same time. Okay, but now what happens when the sun's solar wind and its magnetic field interacts with a planet's magnetic field? This creates what we call a planetary magnetosphere. So first we have one type of magnetosphere that's called the intrinsic magnetosphere. If we have the solar wind from the sun, which we just discussed, that hot plasma that's streaming out away from the sun, and we combine it with that global planetary magnetic field of the Earth that I was describing to you, what we get is an intrinsic magnetosphere. It's called intrinsic because that magnetic field that is diverting the solar wind around the planet is intrinsic to the planet. So this is an intrinsic magnetosphere. So here is a nice schematic that I like to use of the Earth's magnetosphere because we can talk about the different regions and boundaries that are within this magnetosphere. So in this schematic, the sun is situated on the left side where I have this image. And of course, this is not to scale, but it just gives you a sense that we have the solar wind flowing from the sun coming to the right towards Earth in its magnetic field. So the first thing that happens is the solar wind comes across this bow shock structure, this green boundary that you see here. And the bow shock forms because the solar wind is traveling so fast that it's at supersonic speeds. So something needs to happen in order to slow the flow down so that it can divert around the planet. So the solar wind will cross this bow shock and enter this darker blue region that's called the magnetosheath. So the magnetosheath region that I'm highlighting here with my cursor is a region of shocked solar wind. That means that it has been drastically slowed down so that it is no longer supersonic, but it's now subsonic, and the plasma has become densely populated as it's coming up against that Earth's magnetic field, and the temperature also shoots up. And then as the solar wind goes around the planet, this pink boundary called the magnetopause is formed. The magnetopause for this Earth or intrinsic magnetosphere is the boundary that separates everything that is intrinsic to the Earth versus everything that is coming from the sun. Within the magnetosphere, so everything within the magnetopause is considered the magnetosphere here. You'll see we have all these different regions, but we have these yellow field lines from the planet. Everything that is the sunlit side of the planet and the magnetic field, we call it the day side of the magnetosphere. But then, more importantly and relevant to this talk, everything behind the planet and on the night side is what we call the magnetotail. So that's highlighted here in this text. So this is the magnetotail. For Earth, the magnetotail is formed as the solar wind flow goes around that magnetic obstacle. It's just going to stretch the field lines all the way down away from the planet and form this magnetotail. So this is the background on the Earth's magnetosphere. Now, the induced magnetosphere is one that we include where there is a planet without a magnetic field. So we go, once again, we start with the solar wind streaming and emanating away from the sun, and this time the obstacle is going to be an unmagnetized planet such as Venus. So what do we get in this situation? We get an induced magnetosphere, which there's a really nice artist rendition right here of the induced magnetosphere. But let's go ahead with a similar schematic of what I just showed you compared to the Earth. So once again, we have the sun on the left and the solar wind flowing from the left to the right as it's coming into contact with the planets. Again, not to scale, but just to show you the direction of the flow. So in this induced magnetosphere of Venus, you'll see that there are slight similarities and some things that are different when we compare it to Earth. So first of all, we have the solar wind coming up to the planet and first interacting with this bow shock. So once again, that solar wind flow is traveling at supersonic speeds, which means it's faster than the speed of sound, and something needs to slow it down before it comes in contact with the obstacle. So it crosses the bow shock and we enter this magnetosheath region, the dark blue region, and that is where the shocked solar wind takes place. And again, that shock solar wind, the density increases, the temperature increases as well. And the most important thing about this induced magnetosphere of Venus is we want to pay attention to the sun's magnetic field because Venus doesn't have its own magnetic fields. So these yellow lines that you see starting from the left and traveling to the right, those are actually the sun's magnetic fields. And what happens is they will cross over through the bow shock and eventually run up into the atmosphere and the ionosphere of the planet. Now you can kind of think of having a ball and draping spaghetti or pasta over it. It's going to get hung up over the planet, but start to pull back behind the planet as well. And that's what's happening here. So you see these field lines that are strung up on the day side, but then they start to wrap around the planet and extend back. Eventually they will slip over the top and the bottom and continue to flow down away from the planet. But the important thing here is that this is actually creating a magnetotail or a magnetic tail for Venus. So Venus just like Earth, will have a magnetotail stretched behind the planet. However, it's created from a different field. At Earth, that magnetic field is intrinsic to the planet Earth, but here at Venus, this is based on the sun's magnetic field that has been pulled away behind the planet. Instead of the magnetopause, which we see at Earth, we call this boundary the ionopause, but it's still an important boundary, which is pretty much separating everything that is of planetary origin versus everything that's coming from the sun. But then we have these magnetic fields that again form the magnetotail. Okay, so that's your background for the intrinsic and the induced magnetospheres. But now we have this question. Yes?
I'm sorry to interrupt you. There was a couple of questions I was hoping you might be able to elucidate further, which one was just, how is the magnetosphere at Venus induced? If you could describe that. I think you went into some details after that question was asked, but maybe if you could further clarify that. And then, is the bow shock created by the planet moving through space, was the other question.
Sure. Okay. Yeah. So just to reiterate, the magnetosphere of Venus is induced for the fact that Venus does not have its own magnetic field. And so the inducing of the magnetosphere, what that means is that the magnetic field of the sun will interact with the atmosphere and the ionosphere of Venus. And because the ionosphere is filled with charged particles, it's actually going to not only connect with the sun's magnetic field, but also it could generate some magnetic fields of its own within the ionosphere. And so we call it induced because without the solar wind and without the sun's magnetic field, there wouldn't be a magnetosphere at Venus since there is no intrinsic magnetic field. To answer the question about the bow shock is formed because essentially there's plasma traveling so quickly throughout space, like I said, supersonically, and whenever there's an obstacle coming, there needs to be information propagated to those particles to let them know that, hey, there's a boundary or an obstacle coming and we need to go around it. And so a bow shock is the equivalent of, for instance, a shock wave that travels through our atmosphere when jets travel faster than the speed of sound. So it's a shock that forms in order to enable that solar wind to divert around. So it doesn't necessarily have to do with the rotation of the planet. What it has to do with is how fast the solar wind is coming off of the sun.
Great, thank you. And one other question, if you're okay with taking these as you progress. Does the induced magnetic field of Venus provide the same amount of protection from the sun as Earth's magnetosphere?
That's a great question. The short answer to that is no. So one reason is Earth's magnetic field is a lot stronger. And if I just flip back for a second here, for the Earth's magnetosphere, this distance from the surface of Earth all the way out to this edge of the magnetopause is pretty big. It's on average about 10 Earth radii, which gives us tens of thousands of kilometers of space to which we can really hold off that radiation coming from the sun. If we look at Venus here, you'll see that it's much different in this case. So in this case, what we're seeing is the magnetic field can come very close to the planet, but also even when it is close to the planet, that solar wind is able to access the atmosphere. So there really isn't much protection at Venus compared to Earth as far as protecting against the solar wind and solar radiation as well. So it's really the planets that have a stronger magnetic field that are going to be protected against that.
Great, thank you.
Thanks. Okay, so then the question is, what about Mars, the planet we're here to learn and talk about? So Mars is even more complicated in this scenario, and I'll tell you why. Mars has crustal magnetic fields. And so what that means is that Mars does not have a global magnetic field that is protecting the entire planet. But instead, what we have at Mars are localized crustal magnetic fields. And these localized crustal magnetic fields are actually a fossil of a global field that once existed. So we believe that ancient Mars actually did used to have this global magnetic field, and it doesn't exist today. However, what we see are these remnants of that global field that are actually entrapped in the crust of the Martian surface. And so we still have magnetic fields that persist at Mars, but they're in a completely different form. They're patches and pockets. And so I'm showing you a map on the right of these crustal magnetic fields at Mars. So this map is showing you, it has the features of Mars, and then over top, the red and the blue regions are the areas where we have these crustal magnetic fields existing. And so red and blue is just showing you the radial direction, whether these fields are directed out of the planet or into the planet. But the main takeaway from this particular figure here is just to tell you that the strongest crustal fields are located right here in the center where I'm circling my cursor, and that's at 180 degrees east longitude in the southern hemisphere. So the main thing that you should understand about these crustal fields is that they are not uniformly distributed across the surface. They change at different locations, and they have different strengths. And so this actually produces a non-consistent boundary, an obstacle to the solar wind. And so it's ever changing because these crustal fields will rotate with the planet. And to better illustrate this point, I'll flip to my next slide, and you can see this video that we have. And so this movie that I'm showing you is just to give you the sense of these crustal fields and how they're rotating. Now, the location of these fields aren't necessarily what is reality here, but this is just showing you what it's like to have pockets and patches of magnetic field scattered along the surface compared to that figure that I showed you of Earth earlier, where it was a global field. And so what this means is that there are actually just different regions of the surface and of the atmosphere that are protected using these crustal fields. And so this just gives you a nice image here to understand how these crustal fields will actually change that interaction with the solar wind. So with that, I'll show you a similar schematic of the Martian magnetosphere. So I hope I've convinced you at this point that Mars actually presents a really complicated induced magnetosphere. We still considered it an induced magnetosphere because there are these patches of crustal magnetic fields. However, the sun's magnetic field still plays a large role in how it's actually forming the magnetosphere. And like I said, the planet and the crustal fields create this ever-changing obstacle to the solar wind. The interesting thing is that many of the regions that we have that I'm showing you here, and a lot of the processes that we've observed at Mars are still very similar to what we've observed at Earth. However, they have very different impacts on the planet and on the magnetosphere. So to walk you through the Martian magnetosphere here, again, we'll have the sun starting on the left with the solar wind flowing from the left to the right. And we have this bow shock boundary, that green line, where the solar wind is slowed down in order to divert around the obstacle. And again, we have this shock solar wind, which is called the magnetosheath region. But then we have this pink boundary. So this boundary has a couple of different names at Mars. This schematic has labeled it the induced magnetosphere boundary. It's also been called the magnetic pileup boundary or the induced magnetopause boundary. But this is essentially the Mars equivalent of that boundary that defines everything within as being within that Martian magnetosphere. Within the influence of the planet. Everything outside is of solar influence. So the most important thing, other than these crustal fields here, is that you'll notice these yellow lines, the yellow field lines are the magnetic field lines from the sun. They will actually still pass through that induced magnetosphere boundary and come into contact with the ionosphere and the upper atmosphere of Mars. And what that means is that they will drape around just as shown here. So they'll drape around the whole planet. And just as I described with Venus, eventually they'll slip over and they form this induced magnetotail in the back. And so this backside of the magnetosphere is what we're interested in, this magnetotail. So the Mars magnetotail, or the Mars magnetic tail, is the region of the Martian magnetosphere that extends behind the planet. It consists of what we call two magnetic lobes. So one lobe is directed towards Mars, and the other is directed away from Mars. So again, if you can follow my cursor here, this top lobe that I'm circling, this is one of the lobes where you see the arrows are pointing back towards the planet. So when I say directed towards Mars, I mean these magnetic fields are pointing towards Mars. If you follow that field line around, this second lobe here will actually have these field lines pointed away from Mars. So we have what we call two different regions, two lobes of the Martian magnetotail. So here I just want to take a moment to once again really highlight the differences between Mars and Earth as far as their magnetospheres are concerned. At Mars, we have localized crustal magnetic fields, while at Earth, there's a global magnetic field. At Mars, it forms the induced magnetosphere, when at Earth, it's an intrinsic magnetosphere. And at Mars, the sun's magnetic field will influence the magnetotail field direction, where at Earth, it's the planetary magnetic field that will really dictate the magnetotail and what's going on. So now,
thank you, ma'am.
We'll talk about how we're actually going to observe the magnetotail of Mars using MAVEN. And to answer that question, it really depends on two things. It depends on MAVEN's orbit, and it depends on what measurements we have available. So showing MAVEN's orbit here on the left, this is a side view. So if you're standing on the side of the planet looking towards Mars, everything that you see in blue wrapped around the planet, that's actually showing you how MAVEN's orbit has precessed, or how we call move around the planet over time. So as you can see, we sample all different regions of the Martian atmosphere and the magnetosphere here. These lines, this dashed line on the outside represents the average location of that bow shock that I was talking to you about, and the inner yellow line here represents the average induced magnetosphere boundary line, just so we have a sense of where these boundaries are and which regions of the magnetosphere we're sampling. So with MAVEN's orbit changing constantly like this, we have certain orbits where we're able to observe the solar wind so that we can understand what the sun was doing for some of our orbits. So what we're after is to understand how the magnetic tail responds to different changes in the solar wind. What that means is that we need to specifically look at orbits where MAVEN was able to sample both the magnetotail and the solar wind over the course of one single orbit. And so if you look at this, you'll see there are some regions where we're able to monitor the solar wind, and then MAVEN sleeps back into the tail and comes back out. And so we're focusing specifically on the orbits that give us the information both about the magnetic tail and the solar wind. And specifically here, we are using data from MAVEN's magnetometers. So magnetometers are instruments that measure magnetic fields in space. On MAVEN, there are two magnetometers. One is used for science. The other is to help with the calibration of the data to make sure that we're getting the best measurements possible. Both of MAVEN's magnetometers are located on the ends of the solar arrays. So we have a picture of it on the right here. Here's MAVEN's magnetometer, and it's extended off the solar array with this little boomlet here, which is about 0.6 meters in length. So there's one magnetometer on the end of this solar array, and on the other side of the spacecraft that you can't see, that's where the other magnetometer lives. These magnetometers were provided by the NASA Goddard Space Flight Center, and they were actually built in the group that I work at here at Goddard, the group that I work with here. So throughout this work that I'm about to present with you, I've been analyzing the magnetometer magnetic field data. Okay, so then the question is, what is MAVEN telling us about the Martian magnetotail? So the short answer to that question is MAVEN is showing us that the magnetic tail of Mars is twisted from the orientation that we expect it to be. And now I'll convince you why that actually is. Okay, so what do we expect for the tail orientation? We went into this a little bit, but if we assume that the sun's magnetic field will perfectly drape around Mars, we expect that the tail would consist of two symmetric lobes. And so again, we have these blue field lines. This would be the sun's magnetic field that comes and just drapes around the planet and eventually forms this tail. So remember I said there was two lobes. Here's one lobe where the magnetic field arrows are pointed towards the planet. And then there's a second lobe where the magnetic field arrows are pointed away from the planet. So we expect in this situation that these lobes would be nice and symmetric. So we run a simulation to show what that would look like, and this is what we get. So in this figure that I'm showing you on the right, you imagine that you're standing in the tail looking back towards Mars. So if I was standing right here in the tail and I'm looking towards Mars, I would see the red lobe and I would see the blue lobe. So the red lobe corresponds to that region where the arrows are pointed towards the planet, and the blue lobe corresponds to the region where the field arrows are pointed away from the planet. So in this perfectly draped case, this is exactly what we would expect to see. We would see two lobes that are the same shape and size, just with magnetic fields pointed away from the planet and magnetic fields pointed towards the planet. However, when we look at the data from MAVEN, we don't see this. So what I'm showing you on the left, everything on the right stayed the same, but the difference here on the left is that this is the magnetic field data. And so we're able to actually plot the direction of these tail lobes. So if you look at this region in the red that I'm circling, and then we look at this region in the blue, if the field was exactly how we expected it to be on the right, we would see these nice symmetric lobes. But instead, you see this twist, and I can draw this diagonal line with my cursor in between the two, showing you that these lobes are actually twisted away from the direction that we expect them to be. So we did this analysis a little bit further by trying to understand what actually changes this tail twist. And what we found is the sun's magnetic field, the IMF, the interplanetary magnetic field, that is responsible for helping to create this twist, but also to change the direction of the twist. So in the yellow font here with these arrows that I've provided, in the left figure, this is for all of the cases when the sun's magnetic field was in the direction of this arrow to the left here. And we can see that we have that red lobe region kind of coming up into the northern part of the Mars tail, where the blue region is twisted down to the southern region. Now, if we go over to the right, this is all of the magnetic field data organized for times when the sun's magnetic field was directed the opposite way. And you can see there's still a twist, but it's in the opposite direction. So now we have the red all in this left northern area, and then all of the blue in the right southern area. And so we see that the flip has actually occurred based on the direction of the sun's magnetic field. So that's telling us that the direction of the sun, the direction of the sun's magnetic field and the way that it's draping around Mars is actually having an effect on the direction of these lobes, but also the twist as well. So in order to get more information, what we like to do is run models in addition to looking at the data, because these models can give us a sense of what's happening globally. So as MAVEN is orbiting Mars, we're only sampling one point at a time. We're only sampling along the spacecraft's trajectory. But if we can take what we know about that trajectory and use a model to simulate what's going on throughout the entire magnetosphere, it can help us to understand this. So what we did was we ran simulations, we ran models to try to understand if this twist should exist in the tail and help us to understand a little more why it might exist. And let me show you this next slide here. You'll see it looks exactly the same. So the only difference here is that these are simulation results. So what we did with our model was we created this model in order to understand the Mars magnetic tail, and then we flew the same trajectory that MAVEN took around the planet through this model, the simulation space, and created similar plots in order to see what the model would predict. And so now I'm just going to toggle back and forth a little bit between the two so that you can see that the red areas that we observe in the data match up to the red areas that we see in the model. And the blue areas match up with both as well. And so that's saying that even if we don't have the answers specifically from the data here, the models can actually help us to understand what's going on with the magnetic tail at Mars and why it may be twisted.
Gina,
So
there's a couple of related questions,
great.
if I can interject.
Absolutely.
One is asking, does the twist change on the x-axis moving farther away from Mars?
That's actually a great question.
And then the second one is related to that. Does the twist change or flip because of the orbit of Mars around the sun, or is it just the changing IMF?
Great. So the first question, does the twist change with the x-axis? That is actually an outstanding question that I would love to answer one day. There are some limitations just based on the amount of data that we've collected so far. So when I did this initial study, we had, I believe, roughly somewhere around 1 to 2 years of data with MAVEN. At this point, we have 4 years. So I intend on doing this study by augmenting it and adding more data. So more data that we have, more questions we can answer. Right now, with the amount of data that's been analyzed, we're not able to look at it as a function of that x direction that we're asking about. And that x direction will tell us how the tail changes as we move away from the planet. I do believe that that twist will actually change as we get farther away from Mars. However, there just were not enough data to slice it in order to see that. When I tried to make those, it could not convincingly tell me one way or another. But I'm excited to follow up with that and to look at how that changes. And the second question was with respect to the twist based on the IMF direction versus Mars going around the sun. Is that correct?
Right.
Okay.
Yes.
Yes. So it actually really does not have anything to do with the rotation of the planet around the sun, because the IMF changes, the sun's magnetic field changes direction pretty frequently. Sometimes we see it change on the order of 10 minutes or maybe a couple of hours. So it's very dynamic, and that's what's going to have the biggest effect rather than the Mars traveling around the sun. So Mars is really dependent on the sun and the inputs that it wants to provide to us. And to add on to the question as well with the difference in the x direction, one thing that I am also personally interested in is whether this twist in the tail changes as those crustal magnetic fields rotate around the planet. And that, again, is a question that I aim to answer in the future, because if the crustal fields are sitting on the front side of the planet that are facing the sun, you might expect a different result than if they're rotated all the way around and facing the night side away from the sun. So there are a couple of outstanding questions that I hope to answer as MAVEN continues to collect data. So the more and more data that we get, the more in depth we can go with this study. Okay, and we will continue on here. So the natural question is, what is causing the Mars magnetic tail to twist? And the short answer here is a process called magnetic reconnection. So magnetic reconnection is a plasma process that combines magnetic fields. Magnetic reconnection is seen at the sun, it's seen in interplanetary space in between the planets, it's observed at every planet in the solar system. So it's a ubiquitous space plasma phenomenon, and not only does it alter magnetic fields, It also has an impact on plasma. It heats plasma, it speeds plasma up, and it's a really important process that we observe in space. And so for that reason, it's having a really big effect on Mars. So I want to break it down with you what magnetic reconnection is and how it's having this effect on Mars. So like I said, it combines magnetic fields. So at Mars, what it's doing is it's combining the sun's magnetic field with the Martian crustal fields, and it's creating these open magnetic fields. And these new open magnetic fields are connected to Mars, but also open to space. So these colors that I have for you actually correspond to the graphic that you see below. The yellow is the sun's magnetic fields. And then here, this is Mars, this reddish orange planet that we're showing with the Martian atmosphere. The blue loops that you see, those represent the Martian crustal fields. And when magnetic reconnection occurs, it creates these new red field lines. So I'm going to walk you through this in a little more detail, but this is what it looks like when reconnection has occurred. So let's try that again. Here's that equation. Sun's magnetic field combines with the Martian crustal fields, and it equals open magnetic fields. So here's the scenario that we have for the before. We have Mars, we have the atmosphere of Mars, and we have those crustal magnetic fields, the blue fields that you see here. We have the sun's magnetic field as well, the yellow lines here. And at some point, they're going to come together and they're going to interact. So what happens when they interact together? Magnetic reconnection happens. So during magnetic reconnection, these field lines come together and actually create a brand new field line. So this outer blue field line that was once attached to the planet with both ends, what happens is it becomes red for the sake of this graphic. It's still rooted into the surface of the planet, but now since it combined with the sun, the other end is going to be open to space, and that happens on both sides here. So we have these new open magnetic fields. And what this implies is that the magnetic tail of Mars is not actually just made up of the sun's magnetic field draping around the planet, but it can also be composed of these new open fields. And so magnetic reconnection between the crustal fields of the planet and the sun's magnetic field can continue to happen and create these open magnetic field lines. So I can show you on a global scale what that means. That means if we consider the effects of magnetic reconnection, we have a new understanding of the Martian magnetic tail structure. On the left is a cartoon showing you everything that we've explained up until this point, where the magnetic tail is formed because the sun's magnetic field drapes around Mars and becomes stretched behind the planet. But now that we consider that magnetic reconnection can combine the Mars crustal magnetic fields with the sun's magnetic fields, we get this new understanding here where that magnetic tail can actually be composed not only of the sun's magnetic field, but also of these new red open magnetic fields. And these red open magnetic fields are influenced by Mars, but also by what the sun and the solar wind are doing. And so we find that this magnetic reconnection can actually have a big impact on the tail structure. So I'm going to take you back to the original simulation that I showed you, where in the perfect scenario, if we had the sun's magnetic field just draping around the planet, we'd have these nice symmetric lobes. We know that's not the case. But one thing I didn't tell you at this point was that the model that we ran here did not include any effects of magnetic reconnection. So it's something that we can choose to include in the simulations or not. We would love to include it as often as we can because it gives us a more ideal representation of what is actually going on. However, it can make the models take longer to run, and they take longer time. They're more computationally expensive, or you need a better computer to run it. So there are some hardware and software limitations to when we can include this in the model. So for this run, we did not include magnetic reconnection in the model. But what happens when we do? So we decide to include it, and we try to see where these tail lobes will be located. And this is what happens. So when we add the reconnection into our model, we see that that tail twist is now observed. So we've seen the twist observed in the data. We've seen it in some of the other simulations that I've showed you. But now when we're trying to look at specifically these large lobes where they're located, we see that if magnetic reconnection is included, we get this twist that we've been observing in the data. And so that helps us to understand this new tail structure at Mars. And so finally, before I wrap up here, I want to answer the question to you of, why does this tail twist matter? So understanding the tail structure can help us to understand atmospheric loss at Mars. So as we know, one of the main objectives of the MAVEN mission is to understand atmospheric loss to space at Mars and how the Mars atmosphere and climate has evolved over the course of its 4 billion year history. And we want to understand the tail because this can help us to understand atmospheric loss. The reason why I say that is because atmospheric escape takes place through this magnetic tail. So other studies that have been performed by my MAVEN colleagues have indicated that the magnetic tail of Mars is actually a main region where the atmosphere is able to escape. So on the left here, I'm showing you results by Dave Brain, where he has published the densities of the atmosphere getting lost out to space. And he's split it up into day side and night side. So day side on the very far left here is the direction of Mars that's facing towards the sun. The night side on the right here that I'm circling, that's the direction of Mars that is facing the tail, so it's not facing the sun. And if you can see the difference in the colors here, the more blue one square is compared to the other, that means that there's more atmosphere escaping, coming through that region, leaving the planet. And so if you look at the general trends, you'll see on the day side, there tends to be whiter colors, light blue colors, but if you see on the night side, there are darker colors there. So this is telling us that more of the atmosphere is escaping on the night side towards the tail, which means that the magnetic tail is helping to allow these particles to escape from the Martian atmosphere. Then if we move all the way to the right, these are results from Yaoshui Dong, one of our other MAVEN colleagues, and she was simulating the regions where the atmosphere can escape, and then she was comparing it to MAVEN data. And so there are two main channels that she found where the atmosphere can escape. One is through this stream of particles leaving right here where my cursor is on the day side of Mars, and this is called the plume, the atmospheric plume. But her other main region is behind the planet here where my cursor is circling, and that is the magnetic tail. So through other studies, we have learned that the Mars magnetotail is an important region for understanding and observing the escape of the atmosphere to space. So we really need to understand the structure of the tail because this is a region where we're seeing particles lost. And if we understand how the magnetic field is twisted, we can better understand how these particles will escape, because a lot of these particles that are charged are actually going to follow the pathway of the magnetic fields because they are combined together. So we want to understand the structure of the tail in order to better understand where and how the atmosphere is escaping. And with that, I will leave you my conclusions that together here we've used MAVEN observations and simulations, and that's indicated that the Martian magnetic tail is twisted as a result of a process called magnetic reconnection. We find that this tail twist is changing direction with the sun's magnetic field, and it can help us to understand atmospheric loss through the Martian magnetotail. And as I've indicated with some of the questions earlier, this is an initial study that we were able to do with 1 to 2 years of MAVEN data. But since then, we've pretty much doubled the amount of data that we have. So I intend to go back and perform an even larger statistical study in order to answer these questions even more, to see if the Martian crustal fields have an impact on this twist or if it's mostly changes in the sun, and how that twist changes with distance from the planet as well. So thank you for taking the time to listen to me, and I'll take any other questions that have popped up.
Great, thanks, Gina. I've been compiling some questions as we've gone along, so these may be sort of incongruous with where we are in your presentation, but I'm gonna I'll pose them to you in the order that they came in during your presentation. And we have about 12 minutes, so we'll just try to get through as many questions as we can, or I'll leave that up to you, Gina. The first one is, Venus has a molten iron core, but not enough rotation to create a dynamo effect. Is there a minimum speed that a body must turn to generate an intrinsic magnetosphere? And is there a linear relationship between those two?
Okay, that's a great question. So I'll preface my answer with saying a lot of the magnetic field work that I do is actually external to the planet. So dynamo theory isn't necessarily my wheelhouse, but that doesn't mean that I'm not interested in it, because of course that results in the magnetic field generated that I study. So I'm not exactly sure if there is a minimum speed that the planet must rotate, but really what is most important is, when concerned with the rotation, is that you need a conducting core, but you also need that movement around the conducting core to generate currents. So that motion will generate currents. So the speed at which a body rotates probably also is dependent on how conductive that core is and what the size of the body is, but you need some sort of motion to generate the currents. And once those currents are generated, that is when these magnetic fields can be created. And so I think there are a couple of factors at play here, but I don't actually know if there is a specific speed that needs to be met.
Great. Next, how does the solar wind interact with Earth's Van Allen belts?
So the Van Allen belts are radiation belts at Earth, and that is because there are very high energy particles. So this is a completely different scenario than what we have at Mars. So the Van Allen belts are essentially regions of the Earth's magnetic field that are populated with very, very high energy charged particles. And planets like Jupiter also have radiation belts as well. These radiation belts are really important to consider, not only for magnetospheric physics, but also when we consider sending missions to these regions and these planets. Specifically, let's talk about the Juno mission at Jupiter. When you design a mission going to Jupiter, you have to be very much aware of that radiation environment that you could be sending your spacecraft and your instruments to. Same thing goes at Earth, because you don't want to damage your spacecraft at all. So the radiation belts will change drastically when there are changes in the solar wind. And so although the Earth's magnetic field shields the planet and does protect it from changes in the sun's magnetic field and the solar wind, this still changes the magnetosphere. So for instance, when there is a solar event, when there is really, really fast solar wind that's moving away from the sun, it can impact the magnetosphere of Earth, and it can change these regions, and it can actually increase the amount of charged particles that are located in these Van Allen belts. And so there's a huge group here at Goddard where I work that works specifically on these problems at Earth to understand how the sun and changes in the sun can impact the Van Allen belts or the radiation belts. And in fact, there's even a mission called the Van Allen probes that is looking and trying to explore how these radiation belts are impacted by changes in the sun. But it is important to note that despite the fact that Mars doesn't have that global magnetic field, but Earth does have the global field, Earth still experiences a lot of changes based on what happens at the sun.
Great. I'll fold a few questions into one here, but several folks have asked for human exploration, would it be ideal to set up a Mars base in one of these magnetic field, these remnant magnetic field bubbles? It seems nice to live there since there'd be slightly more radiation shielding. And then is Curiosity, as far as you know, is the Curiosity rover under any of these remnant magnetic field bubbles?
Great. So I'm going to just back up all the way to my video, my movie that I showed about. Perfect. And I didn't want it to play, so this is perfect. Okay. So there are a couple of theories going both ways as far as human exploration and using these crustal magnetic fields as shields. And MAVEN is actually one of the ideal missions to study this because we're able to directly observe where particles are impacting the atmosphere and how that relates to where the crustal fields are located. And so it's a tricky question because it almost depends on where you are underneath the crustal fields. So if I can just get this to rotate so it's a little more ideal. Whoops. Nope. Let's see. Okay. So if we see this crustal field right here where I'm circling, we have regions like here in the center and on the outside where the fields are connected to the atmosphere and the planet. These regions are known as the cusps, and they can actually serve as a channel to bring particles down into the surface. So in this region near the cusps or in the center here, it might not be ideal for astronauts or human exploration to be underneath the cusps because the cusps can funnel down some radiation coming from the sun. That being said, in the areas that are not the cusps, that are more horizontal in the field direction, they can serve as those little pockets and umbrellas. And so it's actually an active investigation with MAVEN to understand where solar radiation is able to precipitate down onto the surface with respect to the location of the crustal fields. And as far as the Curiosity rover is concerned, I don't actually have the answer to that question because I have never compared the location with the crustal field map, but that would actually be pretty easy to compare. If you take this map and you find the location of Curiosity, you can look at that. So I can even leave it up for anybody that's interested just to look at the different features of the Martian topography with the crustal fields mapped on top too.
Great. Yeah, I know Dave Brain has done a lot of work in looking at how these remnant magnetic fields have either acted to enhance the radiation making it to the surface or deflect that away. Or
exactly. He is the person that I had in mind when talking about that. He is probably the best expert on that, and I would go to ask him the questions myself too.
I think he did maybe touch on that a little bit during his webinar several months back. So if folks are interested, they can go to our website and watch Dave's whole presentation about how planetary magnetic fields affect habitability. Well, let's see. We have a few more questions. Do we have evidence that the Martian magnetosphere was once more similar to Earth's?
Okay, so we don't have direct evidence because that was billions of years ago. But we have dynamo theorists who have studied Mars and especially what's going on its surface, including potential plate tectonics, which is really getting into an area that's outside of my expertise. But we have scientists actually that even sit down the hallway from me here at Goddard that have studied that in order to understand that Mars likely did have a global magnetic field and that it would have a magnetosphere similar to Earth's. How similar is a good question because that all depends on how strong that magnetic field would have been. So one thing that we're doing on MAVEN is trying to model and explore that because with MAVEN, we don't only want to understand how the atmosphere is escaping to space today, but we also want to understand how it changed over time. And so in order to understand that, we have modelers that are modeling ancient Mars. And when I say ancient Mars, we take models of what we think the magnetosphere looked like at one point in time, and we take models of what we think the sun was like 4 billion years ago, and we have them interacting together in order to understand it. And so with that, I would say if a global magnetic field did exist at Mars at one time, which we do believe was the case, then it would form a magnetosphere that is similar to Earth. Likely it would be on a smaller scale because my instinct tells me that the magnetic field would not be as strong as Earth's is, but it would have very similar regions and properties as well.
Great. Will the InSight lander help this type of research that you're doing at this point? Do you know of any instrumentation or research that InSight is conducting that would be helpful and related to your research?
Sure. So the InSight lander actually does carry a magnetometer on board. And so InSight has landed on the surface of Mars, and we're still waiting for updates so that we can collaborate between the magnetometers. But we actually do have scientists that are associated with both missions so that we can work with our magnetic field data on MAVEN and work with the magnetic field data from InSight and use that as 2-point measurements. So we have a measurement of what the magnetic field is doing on the surface where InSight has landed, and we have information of what MAVEN is observing in the atmosphere and the magnetosphere above that point. And what we can try to do is use those two different data points in order to understand what's going on in between. And so it probably doesn't do too much for understanding what's going on in the tail out away from the planet, but it would be really important for other studies, such as what we were just talking about with the radiation towards the surface and around some of the crustal field areas. And so we will take as much data as we can get in order to understand everything that's going on with the magnetic fields at Mars.
Great. What forces are involved in keeping the remaining atmosphere of Mars from escaping?
So, I mean, there are magnetic forces that will help with containing the atmosphere, but it really has to do with the neutral atmosphere and the gravity of Mars and the energy of these particles. Once these particles gain enough energy, they're able to leave the planet. Once they reach a velocity that is higher than a crucial threshold at Mars, they're able to leave. But if we're talking about charged particles can feel the magnetic field, and they essentially become attached to the magnetic field. So if we have magnetic fields that are draping around the planet, we can actually contain some of these particles that are trapped on the magnetic fields themselves. And so Mars is more complicated than a lot of the planets for the fact that we need to consider atoms that don't have a charge, molecules that don't have a charge, but also charged particles. And so there are forces going on around the whole planet that are playing tug of war. And frankly, it takes the entire MAVEN team and everybody's different area of expertise to try to follow all of these different forces and paths that are possible.
Great. Do you mind taking a couple more? We are at our hour, but if you're okay.
Sure, I have a few more minutes.
More questions. So does the magnetic reconnection process have a significant effect only with crustal fields and not necessarily on a macro scale, for example, with Earth's magnetic field?
Okay, so magnetic reconnection does occur at Earth, and it occurs in the same way. We'll go to
the MMS mission is looking at that very.
Yeah, exactly. The magnetospheric multi-scale mission is looking at magnetic reconnection at Earth. And so we still have reconnection happening at Earth, but instead of these blue crustal fields, it would be that global magnetic field. So essentially, reconnection can occur whenever two different field lines come in contact with each other. So the only difference, and I'm using my hands here, but the only difference that you need is just a slight shear in the direction, a slight tilt between the magnetic fields, and they will be able to come together and connect. And so at Earth, we have many observations of reconnection happening at the magnetopause. And let me go back all the way to Earth now. And like you said, Tom, this is what the MMS mission is exploring. There we go. Okay, so we have observed reconnection happening right here along the magnetopause, that boundary between the planetary field and the sun's magnetic field. So this is called magnetopause reconnection. And when that happens, we have field lines that have one end attached to Earth and the other open to the solar wind. So similar to what I described at Mars. And they will, this open field line will get pulled all the way back into the tail, and that's what actually forms this elongated tail at Earth. Then what happens is these field lines will come down towards the center of the tail in both directions, and they will then magnetically reconnect in the center of the tail here. So when the second stage of reconnection occurs, I wish I could draw on it here, or maybe I can. Let me annotate.
I think if you go to the top, view options maybe, or...
Here we go. I think, can you see that?
Yes.
Okay.
So
awesome.
There it goes.
All right, so here's a field line, and here's another field line, and they've come this way and this way. They'll meet in the center here, and they're able to reconnect. When that happens, the one part of that field line that's reconnected will form a closed loop and return to Earth. So this would actually pinch off and form that closed loop. And then this part would reconnect as well as those field lines combine together and form this other field line that's no longer attached to Earth, and it would get transported away from the planet. So at Earth, we have a cycle of reconnection going on, both on the day side and in the tail. And frankly, it's a little more predictable than it is at Mars, at least for the fact that we know the regions where it will occur. Where Mars, it depends on where the crustal fields are, how they're oriented as they rotate around the planet, and what the strength of the fields are too.
Great. It's wonderful to know you're an accomplished artist as well.
Apparently.
As a scientist.
I should save that.
Is there greater atmospheric loss over the remnant magnetic fields in the south or over the northern areas by way of magnetic draping?
So I'm not quite sure that we have that answer because now let's see, I think I'm stuck in this mode. I wanted to advance to one of my last slides, but I had shown you the global representation that Dave Brain had looked at as far as where the atmosphere is escaping. And so that would give us information. He has the ability to look at that as a function of the crustal field location as well. I don't think that he's done that yet, but essentially looking at these spheres around the planet and seeing what is escaping, that can tell us if it's dependent on the crustal fields. I don't know if he's looked at that, and I don't know if he's seen trends. I would expect that those regions of draped field could also serve to allow particles to escape down the tail, because if they are embedded within the ionosphere and the atmosphere and then stretch behind the planet, then that could serve as a channel that ions are able to stream out from the planet. But I don't think that we have a definitive answer on that. But it's definitely something that we could, and I believe are starting to look at with MAVEN, and we can make some headway.
Great. One more question related to Venus, and that is, have we detected any comparable magnetic tail twist at Venus?
Not to the best of my knowledge. As far as Venus is concerned, I'm not sure if we have the coverage in the tail. I'm not as familiar with Venus missions, but that is definitely a question to look at, and that would be ideal to compare with Mars. My gut tells me that we probably would not see a tail twist because I showed you the original simulation that showed those tail lobes that were perfect and symmetric. And remember, though they were symmetric when there was no magnetic reconnection considered with the crustal fields. But the second that we turned the simulations on with reconnection and the crustal fields, that's where we saw the twist. So I think it would be very important to do that study and to compare Venus and Mars. If we saw the tail twist at Venus, that would be a great indicator that it's not really the crustal fields playing as big of a role as we expect them to play. But my instinct would tell me that we might not see that twist at Venus. However, I'll go on to say that there has been observations that the Earth's magnetic tail has a twist. That is actually still related to magnetic reconnection. And what they've observed with Earth is that there has been that reconnection that's occurred on the day side of Earth and created these fields in the tail. But as it drags back into the tail, when the IMF, the sun's magnetic field, is tilted a certain way, it exerts a torque on the whole tail and can twist it. And so there has been a twist observed in the Earth's magnetotail, which is related to the IMF, the sun's magnetic field, reconnecting with the planetary field.
Great. And final question, Gina.
Okay.
Thank you for staying on with us for a few minutes.
Yeah.
Could MAVEN and MRO data be combined to reveal the composition of the Martian crustal fields, which I believe they already have in some senses?
So we are, I mean, with MAVEN, we are always trying to collaborate with as many missions as possible. MRO does not have a magnetometer to measure the magnetic field. So unfortunately with that, we're unable to collaborate between the missions. But, you know, with our atmospheric analysis that we're doing with MAVEN, MRO provides another opportunity for us to really explore using multiple spacecraft. And so we are, with MAVEN, we're trying to collaborate and work with all of the different missions at Mars, wherever we can, with any of our measurements and our instruments that collaborate well together.
Great. I was trying to answer a couple other things, but lots of questions, lots of interest. This was a wonderful presentation, and thank you for being here, Gina, and we appreciate your time.
Thank you.
I know you have to run off to take care of little ones just as I do, so we appreciate it. For everyone else, if you're interested in reviewing this presentation, please visit our website, which is in the chat, and we'll have another presentation here in a couple months. I'm trying to get someone related to the MAVEN aerobraking campaign. We won't be breaking any news, but we might have some news to share with you about the science findings from MAVEN. So thanks everyone, we'll see you again next time, and thanks for joining us.
Thank you.